what we are going to learn today is like what are the few constructs that enable Docker to do what it does, and we'll see layer by layer how Docker is uh, utilizing Linux primitives to give you a container platform. So a learning outcome from this session would be you would come to know what Docker is, and then differences between containers and virtual machines, and then we'll deep dive into Linux primitives like namespaces and CGroups. These two are the main ones that I will be focusing on. Of course, your production Docker has much more, but if you understand these two, you will be able to make sense of a lot of things that Docker does. Then, along with explaining the primitives, I'll also, go to the terminal and show you how these primitives work, and if you want to try it out, you can try them out as well. And at the end, we'll try to, build a small minimal Docker. This will be in the second part of the session because first session would be uh, like cramping both the sessions together will take away a lot of time, and I wanted to keep it short enough so that it doesn't cause an information overload. Cool. So, does anybody know what Docker is? If someone can quickly give me a gist of what do you think Docker is, and if you have used Docker, then well and good, you can give me a good definition as well. No one? Cool. So, completely new to Docker, even environment over OS. Okay. So, Saurabh is saying environment over OS. That is a good guess. Uh, okay. So, how many of you have heard about that problem? It works on my machine. I hope everyone has come across that at least once. What it actually means, we'll have a look at that. Okay, Mohammed is saying don't know. Cool, cool, cool. No worries. I'll tell you what it means. So you might have faced these issues that you made a software and you were running it on your local setup and it ran very smoothly, no issues. But then you tried to give it to your friend to run it and they ran into some issues. Or even if you say try to download a GitHub repository, build and run it on your local, you see a lot of issues. But the author who wrote all those commands was pretty sure that, oh, I have tried it on my local and it's working. So that's the issue, that's the major problem of it works on my machine, and we'll have a look as to why that occurs. So when you say why it doesn't work on other machines, it can be a couple of factors, a mix of these, or once again I'll admit. Okay, so it could be all of these or some of these, basically a set of these. So maybe your operating system has some different configurations. Maybe you are using a different file system. Maybe you are having some different dependencies than the original system on which the software was running already. Okay, yeah. So all in all, what I want to say is different environments. So what if we were able to, okay, I'll come to that in next slide. So all in all, what I want to say is something that runs on your PC or your OS doesn't mean it will run on someone else's OS as well. And the reason for that could be a mix and match of these different mismatches. So now coming to the question, instead of just the software, what if we were able to ship the entire environment every time? What if you were able to bundle the file system, the dependencies, and the operating system in some sense, not not really, but in some sense, so that you know you get a very consistent run of your software every time. So instead of it not working on anyone else's machine because there was some environment mismatch, what if you shipped both the software and the environment? So in that case, you would be able to run it consistently across any system. So that is what Docker tries to do. That is what Docker does. It solves the problem of it works on my machine and it helps you with shipping the environment. And here I have written automates and the deployment of applications inside lightweight portable containers. We'll come to what it means in the subsequent slides and you'll get an idea of what this statement means. But all in all, just keep this in mind. So whenever you write a software or a utility, the idea is that it is going to reduce some pain points for the user. So Docker here is reducing the pain point of creating containers from scratch for you. It does a lot of heavy lifting in the backend so that you don't have to do those and you can focus on your software majorly with some overhead of writing a Docker file. But yeah, in overall, it does a lot of heavy lifting for you, and we'll see what it does. And yeah, so every slide I have written a fact on the top. You could read this, and these are quite interesting. So the word Docker comes from dock worker or stevedore, which refers to someone who loads, unloads, and manages containers on port. So yeah, does anyone have any questions so far? Environment instance dependent modules. So in a sense, yes, your dependencies, but not only your dependencies, even the file system that you lay out. So when you say environment, not only dependencies, it means dependencies plus file system layout, everything. So you, okay, one second. You might be thinking ki if all I want is to ship my environment, why should I rely on Docker? Don't virtual machines already do that? And that's a fair question to ask. Virtual machines are made to give you, isolated environments, and you can technically do whatever Docker does with VMs also. So if you are just worried about creating an environment, why rely on Docker? Why not on virtual machines? That's a very fair question to ask, and we'll see the differences. Before that, does anyone have an idea of what a VM is? Virtual machine, fine. Okay. So, virtual machines, it'll be better if I explain it in the next slide. We'll see what it does. And yeah, so what virtual machine does is it virtualizes your hardware resources and it allows you to actually hypervisor virtualize your hardware resources and your virtual machine sits on top of it. So basically what I mean is this might be your PC or your what where did it go? Once again. So it might be your PC or it could be your cloud, anything. So what you do is your system is a bit powerful and you want to run multiple different OSs at once on it. So hypervisor, what it does is it virtualizes the hardware resources for you on top of which you run different OS. So virtual machines, if you see this, these two orange boxes and this yellow guest OS box, this entire thing is one virtual machine. This entire thing is another virtual machine, and this entire thing is another virtual machine. So in this example, if you see, you have three different virtual machines running on the same infrastructure, the same physical server. Now, if you see, your operating systems are isolated here. What it means is virtual machines are relying on OS for providing isolation. And what if you look at the image, you'll realize that nothing is being shared across these applications. So you have app 1, app 2, app 3. One second, I'll admit. Okay, yeah. So you have app 1, app 2, app 3, and their libraries and dependencies on top of an OS. But these are all isolated within an operating system. Virtual machines are isolating your applications within an operating system. There are three here, and as you know, operating systems are heavy. You know, can we do better than that? So, if you have a virtual machine, what happens is it takes time to spawn. It requires more memory. Reason being, entire OS is being created for each virtual machine. So you need a lot of memory. You need a lot of resources, and it takes a lot of time to boot up. And if you see, nothing is being shared across these apps. App 1, App 2, App 3 are totally isolated. Other than that, there are a few more challenges associated with virtual machine, such as it depends on the hypervisor platform. Whatever images of these OSS you get, that is dependent on the hypervisor platform. But what's the benefit out of it is you get an operating system level isolation. App 1 cannot interfere with App 2. They will think that they are in their own separate devices. So the overhead what we have here is having multiple OS. And if you see, most of the applications today are based on some form of Linux images. And what if we could remove this entire layer, guest OS layer, and what if we could use the host OS operating system itself? So that is where your containers come in. What they say is, I am not going to create separate operating systems for each of my applications. I am going to use the kernel of my host OS. If you see here, we have one blue layer and your container engine sits on top, and it is simply saying I will use this kernel as my OS. I am not going to create or spawn new OS every time. So that way, what you have done is essentially remove the overhead of kernels from your deployments or your environment. And spawning a container is lightweight. We'll come to this why it is lightweight. One reason you could see right now is, since you don't have an overhead of guest OS, you save on a lot of spawn time, you save on a lot of memory and hard disk requirements. But what's the catch here? Since you're relying on kernel, you get process level isolation, not OS level isolation like in virtual machines. So could be cases that if you do not do this well, or if you do not do this correctly, app 1 could have some malicious intent and it is able to infect your app 2 somehow. So that is the risk of process level isolation, but your container engines these days do this very well, and you don't have to actually worry much about it. If there are issues, that get fixed pretty quickly. And since these are process level isolation and these use, the guest OS kernel, these are trickier to implement and they require a lot of support from kernel. So do you guys have any doubts in VMs?
Yes, I have.
Yeah, yeah. Please go ahead.
So still we are basically operating on OS.
Correct.
So for different OS, it won't solve the problem of it works on my machine.
Yes.
Means the OS have to be same, right?
Hmm, hmm, hmm. We will come to that. That is a very good question. That if I am using the same host OS, how am I solving the problem of isolating my environment? Right.
Yes.
We will come to that. So that is where Linux kernel primitives kicks in, and they provide you ways to isolate a process in a way that process thinks it has its own view of a certain resource. We'll see what that means in detail ahead. But yeah, that's a good question. Jagan has asked, like, you have a separate OS. Difference between VM and partitioning. VM, the OS looks into the entire user memory, whereas the only partitioned user memory is accessible to. Jagan, I did not understand your question. Can you explain it? VM OS looks into the entire user memory. What do you mean by user memory here? Uh, Partitioning and stalling. I am not sure what partitioning is. Do you mean dual boot or something else? Okay, dual boot, right? So you cannot run two concurrent operating systems when you dual boot. You either log into your Ubuntu or you log into your Windows, something like that. With VMs, you could have multiple concurrent operating systems running at once. So that is one difference. And of course, they share the same underlying hardware, but they are being virtualized by the hypervisor, and it gives them a feel of each OS is having its own hardware. So that is how your partitioning and virtual machines are different. In partitioning, your OS actually has access to all the hardware. You don't have two concurrent operating systems running at once when you dual boot something. Does that answer your question? Okay, cool. So earlier I was saying Docker, but I have now moved to the terminology container because container is a bigger umbrella term that covers most of the features that Docker provides, and Docker itself is a container platform. So I'll be using containers from now on. Cool. So I hope you got the essential difference between containers and virtual machines. It's just that you don't have this overhead of spawning a guest OS all the time. Now, before I start with process isolation, uh, I want to know if you guys realize that for a process to run, it requires certain resources, and these resources could be code, file system, maybe your process accesses some network, so it requires network access. It needs memory to run, it needs CPU time, it requires some permissions to perform some sort of operations on your disk, and then your processes communicate with each other, so they do inter-process communication. So when you see a process, it requires certain resources to run. So I have listed down them on my left. And what process isolation means is you're giving each process an independent view of these resources, be it memory, be it files, be it network, users. Users here means your permissions, by the way, and more for each process. So what you are trying to achieve is, if I am saying that I am going to isolate a process, it means that I will be isolating this view of resources for each process. And for a container platform, just isolation of view is not enough. You should also be able to limit the resources that each process use. So all in all, your process isolation is providing a view of the resources on your system and limiting the resources that a process can use. Do you guys have any doubt here? No doubts? Okay. So, by the way, this is an interesting fact. So PID1 in the initial namespace, you cannot kill it. PID1 is basically each process in Linux has an ID associated with it in its namespace, and PID1 is the first process that resides in the initial namespace. If you try to kill it, you'll get a kernel panic. It won't do anything, but it will not be able to kill it. So this is where we now know that our goal is to provide process isolation, and the mechanisms of doing that is by giving an isolated view of the resources and then providing a mechanism to limit the usage of those resources. So first we'll look at how we provide the isolated view of resources to each process, and then we'll go ahead and see how we actually control the usage of resources. So Linux namespaces are a kernel feature that provide the isolation of system resources between each process. Basically what it means is if you have process A and process B and they reside in different namespaces, they won't be able to see each other. So in layman terms, this is what it means. And as I discussed earlier, there can be multiple different types of namespaces depending upon how your like what resources an operating system is interacting with. PID is a process ID namespace. User is your user permission namespace. Mount is your file system namespace. Net is your network stack, TCP/IP network stack namespace. UTX I think is your Unix time sharing I think. IPC is for inter-process communication. C groups will come to that later, and then we'll see what C group namespaces are. So basically, when you start a process, each process on Linux is associated with a namespace of each type. So if you have a process, it will be associated with uh, each of these namespaces. And let's quickly have a look at what I mean with that. So basically, if you see, this is a shell, this is a process, and this is the ID of that process. So if I see, if you want to see the namespaces associated with this process, what you can do is uh, you can simply do this, and this command basically is a symlink. We'll come to this later again, and just to show you that each process resides in namespace of each type, I have shown you the command here. So you can see it is in IPC, mount, net, PID, time, user, UTS, C group, all of these. So is it clear? Okay, no comments. Cool. Moving ahead, we now know what a namespace is. But if you go to the Linux source code and see what namespace is, it's basically a struct. I have added the once I shared the link, you can click on this and view the Linux kernel source code as well. But most of your namespaces, I think 5 or 6, are within this NS proxy struct. If you see UTS namespace, IPC namespace, mount, net, and time and C group, all these are in your NS proxy struct, and this NS proxy struct is a part of each process, is a reference to your process ka struct. Basically, each process in your Linux operating system has a task struct, and it holds a reference to this NS proxy object. Count here is used to count how many processes are referring to this namespace proxy. So just to give you an idea of what uh, NS proxy is and how it looks. I have added this. Even if you don't know this, it won't affect your understanding of how namespaces works. But it's good to go and have a look. So yeah, going ahead. Right. So now we have learned what namespaces are. Its job is to uh, give the process a isolated view of the resources. So the next thing is, how do I actually interact with namespaces? Right. So whenever there is a kernel feature, how you actually interact with them is using system calls. And system calls are made by applications in user mode, and then your access goes to the kernel mode and it is able to execute those commands. So we have three ways of interacting with namespaces. We'll look at unshare today. And I've listed these down here. Clone basically creates a new process, and it it gives you an option to create these processes in new namespace, or it could inherit the namespaces from its parent itself. Unshare is how you detach a current process that is running from one or more namespace and create new namespaces on top of it. Set namespace is how you enter into a process which is already running into a separate namespace. So if you have done docker exec some container and then ran some commands, it uses set namespace internally. We'll look into that in the next session. So moving ahead. So we'll look into two major namespaces today. Uh, One is the PID namespace, which is a process ID namespace, and the second is the mount namespace, which is your file system, which basically deals with your file system mount points. Not even file system, you could say mount points. Yeah. So PID namespace, what it means is, this namespace, what it does is it isolates the process ID number space, and it means that each process in different PID namespace will not be able to look into the other processes. So first process in each PID namespace is given an ID 1, and then this uh, this this namespace is actually special because it is hierarchical in nature. What I mean by that is, each process will have a separate process ID in all of in all the layers of namespace. So you could imagine, let me see, you could imagine process ID namespace as a tree where you could have one namespace, say this is one namespace, and you create another namespace out of it, and that would be the child of this namespace. What I mean by that is, within each subtree, you can have same process IDs. Is that clear, or do you guys have doubt in that? Since it is hierarchical, what it means is you have a parent-child relationship, and processes in your child namespace, cannot see the processes running in your parent namespace. But your parents can have a look at your child namespace, and they can see the processes within your child namespace. Although the IDs that the parents see will be different from what the child see. We'll look at what this means with more detail when I go to the demo part. Someone has a question, I think. No one?
Yeah, I have.
Yeah, yeah,
Child process have a different PID and parent process have different PID, correct?
correct.
Okay, so but now you said just now you said कि child have same PID as parent.
Not as parent. What I said is, if you have a child in a different namespace than parent, then it can have the same PID.
Okay,
Basically, each namespace, your PID starts from 1 again. So if you have a process in a new PID namespace, and it is the first process, it will get ID1 and then it will sequentially increase. But in the parent namespace, the process ID of that child would be different.
Okay.
Yeah. So, and the by the way, the way you can create this new PID namespace is if you use unshare, you can give it a flag saying PID and it will know that it has to create a PID namespace. We'll look into this in more detail when I go to the demo part. Uh, but if key thing to take away from here is you have a parent-child hierarchy in a process ID namespace, and parents have a view of all the processes, but children do not. What PID namespace is actually used for is for migrating containers, since each PID namespace has its own view of process IDs. You can technically isolate a process ID namespace, move it to a different host, and then resume their working, and they won't actually realize that they have been moved, because within the PID namespace they still have the knowledge of the process IDs that they were actually using earlier as well. So before going into the demo, PID1 is actually quite important, and that is why I have made a slide for it. So first process in a PID namespace gets ID1, and you could think of it as the owner of the container, and it has some responsibilities. So what responsibilities does PID1 have? PID1 within a namespace has the responsibilities of cleaning up all your orphaned child processes. Basically, when your child processes within a PID namespace, say the parent of that child process died, then your PID1 is responsible for cleaning them up. And if it is not cleaning up, you will get the issue of zombies accumulating and memory bloat. So that is the responsibility of PID1. Since it is responsible for being the last process to exit, you can see why it is the last process to exit from a namespace, because it it needs to clean up all the orphan child processes before it exits. So since it is responsible for that, you your PID1 cannot be killed easily. Basically, what that means is you have to register signals for process if for PID1, and if you don't register those signals, it will not get killed. It can be killed only from a parent namespace. It cannot be killed from, say, the same namespace. So, uh, like I was mentioning, you cannot kill the PID1 on your Linux OS. You get a kernel panic. Similar to that, you cannot kill the process one within a PID namespace. It will not work because it is responsible for something. Does that make sense? Uh, no doubts. Okay. So I'll quickly show you what namespaces means and all these things. So before that, how many of you know what virtual file systems are in Linux? Anyone? So in Linux, actually the way you interact with a lot of things is using file systems. And virtual file system means that you don't actually have files on the disk. It is generated by kernel at runtime. So the process that you see, the one that I showed you, this thing that, by the way, this is the root directory. I hope everyone knows what a root directory is. And within the root directory, you have this slash proc folder, and this is a virtual file system. And information about each and every process running within your system resides in this folder. So if I do an ls, you will see a lot of numbers in this folder. Is it visible? Is it clear? If not, I can actually close these so it becomes a bit more clear. Is it clear? Okay, but then you won't be able to. Okay, I'll write it here. I think it will be clear here. Uh, so if you see, you have a lot of PIDs here. Each PID is a number, and the way you can see running processes on a system is by PS. This gives you details about not all the processes. If you want all the processes, you can do PSEF. Yeah, and you can see all the processes running on this system currently. So slash proc is a virtual file system, and you actually interact with it similar to how you would interact with a file system which uses on-disk files. So that is the benefit. You can use tools like cat and ls on this and virtual file system, and it works. As you can see, it's working. So now I'll quickly show you what does it mean when you say that I create a new PID namespace. So sudo unshare. This is the same command by the way that we had back there. Okay, just before that, I'll quickly. Uh, this is a special variable in your Linux which returns the process ID of the current shell. So this is the current process ID in the parent namespace. Now what I'm going to do is, this is a running process. I will unshare the PID namespace for this process, and then we'll see uh, how it looks. So now I am in a separate namespace. What I mean by that is, if I do PS here, okay, one second, should have an, and okay, my bad, I have shared the mount namespace instead of the PIT namespace. Yeah. So if you see here, my bash, which was originally 488467, this was the original process ID in the parent namespace. As soon as I unshared and created a new PID namespace within the namespace, now I am in the child namespace, and I cannot see all the processes in this namespace. I am only able to see the processes uh, that are in this namespace, and in this namespace I only have one process running, that is the bash. This is your command that you run. So since I am running PS here, it's coming, and you can see that PID is increasing every time. So yeah, you can see that in the parent namespace I had a different PID, and in my child namespace the PID is different. By the way, if you still feel that I am not convinced if these are like within the same namespace, you can do one more thing. This is the process ID of this shell, and this is running in the parent namespace. By default, everything runs in the parent namespace or initial namespace. So what you can do is, you can read the namespace, PID namespace for this, and what you see here is, this is the inode of your PID namespace for the initial namespace or parent namespace. Dollar dollar here is your process ID of this shell. Now what happens if I do the same? I read the same file for my this process, which is in a child namespace. If you see, these are two different. Okay, no, not really. Once again, should be different. Huh. Okay, let me see. Why is it not different? Uh, this was different. You'll get one here. Okay, I'll come back to this. Actually, these IDs should be different. Not sure why it is not different. When you unshare a process ID, it should be different. So yeah, I'll come back to that later. So that is what I had to share about PID namespace. Does anyone have questions in this? I think you guys would have questions, but not sure. Even if you have questions after the session, you can send it on the group, and I'll have a look at them. I'll moving ahead. Now we'll move on to your uh, mount namespaces. So as I said before, mount namespaces provides you a separate set of mount points, and what it allows is it allows you the processes to have a different view of the file system hierarchy. And the way you actually unshare a mount namespace is using this command hyphen hyphen mount. I think shorthand for this is hyphen m. You can use that also. So if you have run Docker and all those, you would have seen that within an container, when you go inside and you do a ls, you have a very different file system from what you actually run on your host OS. So that is a feature that is possible because of mount namespaces. So each process will get its own view of the file system, and then since it is having its own view of the file system, you can mount any file system there. So that is what mount namespace does. It gives you a chance to mount your own different file system, a different folder structure, which is different from your host operating system. So more on namespace. Basically, each of the Linux process, if you see, it expects to have access to this kind of structure. It needs a root directory. The slash is a root, and it needs a few binaries in its bin directory, temp, where, proc. If it doesn't have access to all these, it won't actually work properly. So I've just showed you here what a process needs to uh, work properly. And if you are isolating a mount namespace and mounting your own file system, you have to make sure that you provide the uh, process with these directories. Not all of them, but some of them. Yeah. So coming to this, if you just isolate your mounts but do not change the root directory, what it means is that your process will have access to the original root directory. It will still be able to access that. And if even before showing that, we can validate that here. So this process and this process, now these two processes are in the same initial namespace, and both have access to root. So you can see that both are able to access the root directory. And if I simply create a new mount space and I am not giving it a new directory and not doing those stuff, then your new process will still have access to the root directory, which is not what you want. So mount namespace on its own is not very uh, complete. You actually need a bit more. You actually need to say that once you have created a new mount namespace, you actually provide it with a new root directory. You actually provide it with a new file system. If you don't do that, then your process has access to your original root directory, and if it has access to that, then it can do anything it wants. It can go and change some host files or something like that. So in a container, when you say that I am going to provide you complete isolation, you have to make sure that you don't run into this issue. So that is where uh, pivot root and a few more commands come in. We'll have a look at those in the demo. Any doubts in mount namespace? No doubts?
I have one doubt.
Yeah, yeah.
So, like, what all namespace are essentially necessary to make our own separate process? Like you mentioned, we need
Ideally,
money.
ideally
Mm,
you would want to isolate your process from everything.
mm,
So ideally you'd want to do all of those, but I think Docker, as far as I know, does six of them by default. Two of them it does not. Time time namespace, I don't think Docker has that. But yeah, other than that, I think Docker does all of them. Time and one more.
oh,
I'm not sure what is that one, but other than that, you need to isolate all the namespaces.
okay. And this mount namespace,
Mhm.
so by default, is it stored in a RAM or like it's stored in a SSD or let's
It
say?
depends. So
Okay.
wherever you point your slash root directory to, if you
Mm-hmm.
have an implementation of in-memory root file system, you
Okay.
can point it to that. If you have on disk and you say you extract the rootfs folder in within some subfolder within a directory, you are extracting a rootfs folder and you're pointing it to that, then it's actually on your file system. So it could be either.
Okay. Got it.
Okay. So this is very important to know that if you have a root namespace and if you're just isolating a namespace, it's not enough. You actually need to say to the process that from now on, this will be your root and you have to access files from here only. You should not be able to access your host root. We'll see how we do that in the demo. Moving on to the demo. Okay, very next slide. So previously I showed you how process name PID namespace works. Now I'll quickly show you how mount namespace works. Uh, I actually have this directory. Let me see what's there in this. Okay, it's empty. Cool. So I'll just change to that directory and I'll create a small file and write it to some file, say docker.txt. Now if you see, this file is in the initial mount namespace. It's visible in both the places. Now what I want to do is I will create a folder here and I will create a new mount namespace. I will tell the process that this is your root from now on. By doing that, it will not be able to access the original root. Basically what it means is if you do a cd change directory to root, you see something here, but if you change directory to root after you have isolated the mount namespace, you won't be able to see this directory. Uh, okay, cool. So what I want to do is, cool. I'll first create a new mount space. The way you do it is very similar to how you did the PID one. You basically, one second, someone has joined. Someone joined, right? Someone, okay, maybe they left. Cool. So, yeah, I'm unsharing the mount namespace and starting a terminal there. Once I have done this, I actually need to tell my by the way, yeah, before that what I can do is I can show you. I can create a file here, say patch docker2.txt, and since I have not isolated my mount points yet, whatever changes I make here would be visible in my original namespace also. So to avoid this from happening, I have to say that make this mount private recursively, so that whatever changes I make here are not visible here. So the way you do that is you actually have a command. So make, what you are saying is whatever changes I make to the root that this uh, process is associated with will not be propagated ahead to any of the namespaces, mount namespaces. Now, just to show you, what I'm going to do is I'm going to mount a temporary file system. So tempfs is a virtual file system like your slash proc, and whatever changes you actually do here, those will not be visible outside. So let me quickly show you that. Now if I create a new file, say, I hope it works because the first time it did not. Okay, there is something missing. I'm not sure what is missing. I'll have a look at it. But this is one thing. And there is one more thing I have to show you. I'll quickly remove everything. Yeah. So I talked about pivot root very briefly. I'm not sure why it keeps up showing here. Maybe I'm missing a step. I'll have a look at it and I'll let you guys know in the next part. Not sure why uh, even after making the mount space uh, private, it shows up here. Not sure why that is happening. So anyways, I'll quickly show you the other part where you actually mount a new file system. Okay. So I have this thing called BusyBox static. You can think of it as a minimal Linux binary with all the functionalities, ls, cat, those kind of things. So those kind of things are present in this binary. So I've just extracted it here. Now I'll create two new directories, uh, binary and put old. Yeah. So I've created two directories and I'll just copy whatever is in my binary to there. And now what I'll do is I'll have to change the executable permissions for that. Now I'll create a new uh, mount namespace. So I have unshared and created a new mount namespace, and it still points to the uh, basically you can still do this and it will still point there because we have not changed that setting yet. So let's do that quickly. Okay, yeah. So after unsharing, I'll make the mount namespace mount points private. Okay, and then I'm going to say that this directory is I'm simply mounting whatever I have in my Docker home new root to itself. I have mounted that. Now if I change to new root and yeah, so what I have done till now is I have just set up a few things. I have a binary folder here. Now what I can do is I can pivot the root for this process and say that this directory is going to be the root. What I mean by that is once I run this command, I will not be able to see the root outside. I will only have access to this as my root. How you actually do that is you use this command called pivot root, and what I am saying is this current directory will become my new pivot root. Put hold is an additional parameter that pivot root takes, and what it means is where should the process have the reference to your previous root. So now that I have run this command, what actually happens is it will try to fetch all these commands ls cat. I'm not sure if cat works. Yeah, see, cat is not working, ls is not working. Why this happens is because as soon as I have pivoted my root, it will search for all these binaries in this folder /bin. And if you see this /bin, what it actually has, let I'll just quickly show you what these have. It just has busybox. It does not have ls or cat, so it's not able to access those. And so now what I have done is I have successfully changed the root of this process from the parent root to this directory, new root directory. Now I can quickly show you. Basically, I installed busybox because it gives you all those commands. Now if I do change directory to slash, it is not escaping to the parent. If you do it here, it shows you the initial namespace root directory, but here since I have pivoted the root to point to this directory, I am not able to escape it. I still have the contents in puthold. If you want to see, I can show you. You can still see those, but it's just a matter of unmounting that directory. You can unmount the puthold directory. Okay, once again. Since I am forcefully unmounting it, actually you don't use -l flag, but for demo purposes it is fine. Now if I say do a cat, not cat, ls puthold, you will not be able to see the root directory at all. So you have successfully jailed your process into viewing the root as this directory only, and it has lost all the access to the other outer directory. I hope this makes sense, and I hope you are able to get an intuition as to why this is important. You create a new file system and you are now forcing your process to believe that this is your root and you have no access to outside. Here I have created these two folders on my own, new root, and I've added a binary there. You could have a full-fledged file system here and it would work. It would not escape to this now. It would actually work within this. And so this process has now gained a very isolated view of the file system using mount namespace. Is it clear?
Yes.
If you have doubts, we can discuss those. And yeah, so this was a crucial one, mount namespace. So basically, what your Docker does is if you are spawning, say say Docker run Redis or something, it will create a mount namespace. And instead of creating a new root or a directory that I did, it will create a full-fledged file system there in some directory. I think by default it is docker where slash var slash docker where all your file systems reside. I might be wrong, but yeah. So Docker is doing this thing, but on a bigger scale. Here I was able to show you isolating a root mount a process to have its own view of its own root. So in essence, this is what Docker does, and this I feel is the most crucial part of isolating a process. If you mess this up, then things can go wrong. You can escape to your host file system and you can do some bad things there. So this, according to me, is the most important namespace when it comes to containers. So far we have discussed process ID namespace and mount namespace. Next, we'll quickly have a look at what control groups are. So in the beginning, I said that each when we talk about process isolation as a task, it involves two components. One was providing each process an isolated view of the resources, and another was how you actually limit the usage of the resources for that process. So namespace were solving the first component and control groups solves the next component. So CGroups are a Linux kernel feature that constrain how much resource a process can use. And it also not only limits, it actually even gives you an statistics of how much resources a process is using. So it limits and it accounts for the resources used by a process. And then C groups are hierarchical in nature. You can have C groups inside C groups, and what that means is you can distribute resources basis weight. So say you had a parent C group which could utilize 50% of the CPU time. You could have two child C groups within them, and say both were allocated 50% of your CPU. Then from your actual host CPU, those two child C groups will get 25% of CPU time because your parent gets only half of whatever CPU time is available, and it's further divided into half hierarchically. Two C group versions exist today, V1 and V2. We will demo it with V2 because my system uses V2. And one more interesting point here is V1 in V1 version of C group, a process could be part of different C groups for each type. What I mean by that is you could have a C group for CPU, you could have a C group for memory, you could have a C group for disk IO, for network, all those. And a process could be separately be a part of all of those. What it did was it used to create confusion when it came to limiting. There were conflicting trees. So a unified version V2 was released. And what V2 does well is it says you create a C group. That C group will have all the different kinds of limiters and usage controllers in it. You cannot have a process in two different C groups now. It will be it will be in a single C group, and the all the controllers will be in the same C group. Basically, that is what V2 has done. It has given a unified interface for C groups. Coming to controllers, what controllers are? So basically, these are kernel modules that are responsible for enforcing limits and collecting metrics on specific resource. So we have 9 types of C groups and 9 types of controllers for these. CPU and CPU account were merged, I think. Yeah, these were merged in V2, unified in V2. So CPU and CPU account deal with your CPU time. CPU set actually deals with if your process wants to pin a memory to a certain CPU. I am not very sure how it works, but if you want your process to stick to a certain CPU and it sticks to using a certain memory, then you use CPU set. I don't think this is useful for most of the applications, but yes, it exists. We have memory controllers for memory. Block IO deals with throttling and limiting usage of how much IO a process can do on disk. Net is for your network resources. Devices here means all the devices that are connected to your system, both virtual and physical. Freezer is used for suspending all the processes. It comes in handy, I think, when you do container migrations. Uh, but for understanding, I don't think you need to know how it works. PID uh, is basically a controller group which helps you determine how many processes a group can have, and you can control those sort of things with PID controller. And then you have huge TLB. Huge TLB is huge pages. So huge pages is a concept that was introduced, not sure in which version, but what it says is instead of having very small 4 KB pages, I can have large 2 MB pages or 1 GB pages, and huge TLB deals with that. How do you limit access to how many TLBs you can create and stuff like that. So this comes in handy with in database applications. Not sure if it comes in handy in your certain web applications. So these are the 9 controllers we have, and it's very interesting. And the demo is also pretty nice for this. So let's quickly have a look at this. I just want to close all these terminals because I don't want it to. Yeah. So coming to we'll do this today. I will show you the demo for two C groups. One is your CPU and another is your memory. These two will give you a very nice idea of how C groups work and what they are actually doing. So just if you want to check what your C group version is, you can run this command and it will say that type of C group you have. So my kernel currently is running on C group version 2 by default. Yeah, so before moving on to the CPU C groups, I quickly want to show you where does this actually reside in your system. So sys slash fs slash C group is where your C group data resides. You can actually change to that, and even this is a virtual file system. What it means is there is no actual file on the disk. Everything is created in the by the kernel on runtime. So if you see here, you have got different kind of files here. CPU dot stat, CPU dot stat local, CPU dot cgroup dot procs, and then memory dot pressure. All these things are present here. CPU dot pressure. Basically, you can read these files if you want to see. Cgroup dot procs contains the process ID of all the processes that are a part of this C group. Since this is the parent C group, you'll see all the processes that are part of this. Now what I am going to do is I am going to create a new C group here, and it's pretty easy. You can simply create a directory, say let me call it my limits. Of course you need permissions for that. Yeah. Now if you see, there will be a new directory created here called my limits. You can change to that directory, and all the files that you saw in the previous directory will be created here as well. Not all the files, but most of them. So if you see, you got files like cpu.max. What it means is what is the maximum CPU your your process can use. You will have something here for PIDs as well. PIDs.max. What it means is how many processes you can spawn within this uh, C group. So the name of the C group is the name of the directory, and you have these files to control the usage of resources within that C group. Now what I am going to do is I am going to limit the number of processes that can be spawned in this C group. I'll limit it to 5 and I'll write it to PIDs.max. If you see PIDs.max is 5, whatever I wrote here. So I cannot spawn more than 5 process in this. So I'll quickly change to C groups. Okay, no need, I'll do this. Okay. So what I'm now going to do is I will move this process to this C group. And how you do that is I mentioned a file earlier. Was it procs? I think it was. Is it visible somewhere? Cgroup.procs, right? Yeah. So if you see this cgroup.procs, it's empty. Basically, there is no process associated with this cgroup. What I'm going to do is I'm going to move this shell in this cgroup now. How you do that is you have to echo this process ID into this one, and I'll have to change the name of the file folder. Now, now this C group, this process is a part of my limits C group. Now, if I do this cgroups.process again, you can see this is the new single process which is present in this C group. Moving ahead, I was able to successfully put a limit on PIDs.max and even move it to that C group. What I will do now is I will show you this in action, and what this command does is it spawns a child process, and let's do it for 10 seconds. 100 is too much, and it runs it in background. Okay. How is it failing? We have 5 processes, right? Okay, so if you see, these processes are running here, but it's not very clear. uh, Although we have a limit of 5, it is not able to. Okay, I'll do this. I'll do it everything at once. For I in 1 to 10, do. We'll sleep for 5 seconds and then done. Let me increase the limit. All of this worked earlier, but as you say, during demo nothing works. So that is what is happening right now. Okay. Okay, not cgroup.pros, PIDs.max. Okay, maybe from here if I say echo 10, what was the command? I did make it 5, right? Yeah, it is 5, so it should be able to spawn 5 processes. Let me close this. Not sure if this should not affect it, by the way. Uh, I'll try to run this and see if it works. Now it's a bit more clearer. So if you see, I had a limit of 5 processes and this loop spawn was trying to spawn 10. So I was able to spawn 4, and since this process is also a part of this C group, 4 plus 1 5, it was not able to spawn anything more than that. So you get this error, resource temporarily available, and then it fails. So what you have essentially done here is, for this C group you were able to limit the number of processes you can spawn and the number of concurrent processes that can be present at once. So another interesting thing is you can actually uh, watch all the PIDs that are running currently. Why is it one? Okay, maybe that runs by default. So, so okay, I exited quite quickly, so I'll just show you. Currently it is 1, and as soon as I run this script, it becomes 5. So it shows you count of how many processes are running, and as soon as this finishes, it again goes back to 1. So pretty neat how you can control within a C group how many processes you can spawn. This is helpful to protect your host OS, since isolation is being done at a process level. If one malicious container is executing a fork bomb, you don't want it to affect all the other containers. So this becomes very useful in such cases where you don't want one container to hog up all the resources of uh, that may be useful for others. So this was a small quick demo on PID's controller. Next we'll have a look at the memory controller. So I will quickly do this. I will, so basically what I'm saying is this is 1 MB. So if you see the file here, the file is memory.max. It is set to max. So basically it will take up all the RAM that I have. So I am going to say no, you are only allowed 1 MB of RAM for this C group. And the way I do it is similar to what I did in the PID's case. Uh, what was it? Says fs C group my limits memory dot max. Basically, you can also set a min, but that won't show you the actual demo. So now it has 1 MB of memory, and I have a utility here which basically hogs up memory, and I'll show you. So stress is the name of the utility, and I am going to start one background worker for this, and I am trying to hog up 50 megabytes of memory and trying to keep it alive for 10 seconds. So let's try to see if it works. If you see, it tried to do it, but it got a signal 9. Signal 9 is an exit signal, and this was actually sent by this controller, memory controller, to this process saying, bro, you are only having 1 MB of memory. You cannot use 50 MB of memory. So out of memory killer got triggered. Basically, that has resulted in exit of this process. And one more point, this out of memory killer first does a soft warning and it notifies your process. You can actually have event handlers for that on this process. But if it still increases, if the memory usage still increases, only then it kills. So it's sort of a soft limit, but if it goes out of range by a lot, then it kills your process. So this is how you are able to control CPU, number of processes, a number of memory, and a few more other resources that your uh, process might use. So pretty interesting how they have thought about all these and implemented it at a kernel level. So to sum it up, Docker is using a lot of powerful kernel features to provide process level isolations. We've looked at two of them, and I tried to explain two in each of them, namespaces and CGroups. Namespaces are restricting the view of resources. CGroups are restricting how much a process can use. By process jailing, what I mean is how well you are isolating it from the system so that it is not able to create a jailbreak and escape to and affect your host operating system. So process jailing is important. Whatever I have done today, you can do it and you can actually create a container of your own without Docker also. But these platforms make stuff easier for you, and you don't want to actually do this stuff because it's risky. You might end up messing some stuff. So it's better if you use a container platform that does these things for you and makes your life easier. But it doesn't hurt to go under the hood and have a look at the technologies that are actually powering these containers. So that is uh, all that I had to share today. Part 2, I'll explain to you what Open Container Initiative is, and then we'll implement the runtime spec of OCI, and we'll see how you can do whatever I've done today using system calls a bit more programmatically and a bit more neatly. These are a few references that I used for this presentation. If you have time and if you are interested, I'd definitely suggest you to go through these. These are very detailed and very well written. So have a look at these and we can discuss further if you guys have any doubt. Yeah. So any questions, guys?
Uh, when will the next session happen?
Next session, I am not very sure, but I will try it in next 2 weeks.
Okay.
I have some work next week, so I am pretty sure not next week, but yeah, next to next, I should be able to.
Okay.
Yeah, cool, guys. Thanks for the session. Thank you guys for attending. If you have any doubts, just hit me up on the group and I'll answer it there. Cool.